So in this section, we're going to examine how the electrons are arranged in an atom, known as the electronic structure. Now, why do we care about that? Well, we need to know how the electrons are arranged so that we can understand the next two chapters, which are dealing with why atoms of one element will stick to atoms of another element to form bonds. So for example, when two atoms collide, it's the electrons from one atom on the outside of the atom that are going to interact with the outermost electrons from the atom of the other one. So it turns out that two things can happen. An electron can be transferred from one atom to another, and somehow that leads to stickiness or a bond. The other way is that the electron clouds interpenetrate, so that electrons are actually shared between the positively charged nuclei of the two atoms. And somehow that also leads to stickiness. But either way, we need to know how many electrons are in this outside part and how tightly are they bound to each atom. The other thing that we'd like to address is this periodic pattern that we see in the table of the elements called the periodic table. This periodic pattern is namely this one. Why do elements in a group have similar chemical properties? So what do we mean by that? Well, if we look at group 1 and 2 elements, we'll just look at lithium and sodium. You can keep on going down to potassium, rubidium, and cesium, beryllium, and magnesium here. And how about group 17 elements? We'll look at fluorine and chlorine. So these are metals. These have the property of being nonmetals. What we're going to see in the next chapter is that when metals interact with nonmetals, you'll form compounds. And if we look at the compound between lithium and fluorine, you get this type. If we do sodium with fluorine, we also get a formula of this type. So what do we mean by these formulas? Well, it turns out that the number of lithium atoms and the number of fluorine atoms in the compound are equal. It's 50-50 mixture. So we call this a 1-to-1 number ratio. So sodium and fluorine form the same 1-to-1 number ratio. And if we look at this with chlorine, we get the same thing. We get a 1-to-1 number ratio for both compounds. So this is a periodic pattern. We're saying that lithium and sodium behave in a similar way when they form compounds with fluorine and chlorine. And we could also say that fluorine and chlorine formed a similar pattern when they react with lithium and sodium. Beryllium and magnesium also react. When beryllium forms a compound with fluorine, the number ratio is 1-to-2. You need 2 fluorine atoms for every beryllium. In magnesium, you see the same thing. And we get the same behavior with chlorine. So we're saying that, for example, lithium and sodium have similar chemical properties just to the extent that they form the same number ratios when they form compounds with other elements. Same thing with beryllium and magnesium, and same thing with fluorine and chlorine. Now, what we're going to show you is that the theory that is going to allow us to determine how the electrons are arranged in an atom to allow us to start to discuss chemical bonding, as well as this experimental property that we see that elements in similar groups, elements within a group in a column have similar chemical properties, derives from a very successful model of reality called quantum theory. It works for describing matter at the very tiniest of length scales and mass scales. So we're talking about, what we care about here are the electrons. So we need this theory. We're not going to discuss the interesting things about quantum theory. Instead, we're going to go straight to the results that come about from this mathematical model. And the result is this: the electrons are arranged in concentric shells about the nucleus. So let's take a look at this. So before we begin, it's important for you to pay careful attention to anything that is in bold. So you're going to see some new language, and you need to be aware of the definitions and to not get these definitions confused. So first of all, the nucleus is at the center. It's positively charged and is given by the atomic number Z. So the total amount of positive charge at the nucleus depends on the number of protons. The electrons are arranged in a cloud around the positively charged nucleus, but quantum theory states that they're arranged in very specific ways. The first so-called shell is labeled n is equal to 1 by the quantum number n. This is a region of space where you can find the first electrons. It has a certain capacity to hold electrons, which we'll talk about later. But when this is filled, any extra electrons have to be in the next shell, which we call n equals 2. Note that the next shell, so when this is filled, you begin to fill the third shell, and when the third shell becomes full of electrons, you begin to fill the fourth shell. Now, the other important thing to understand is that the closer the negatively charged electrons are to the positively charged protons, the more tightly bound the electrons are, because they're experiencing a stronger force of attraction. The closer the positive and negative charges get to one another, the stronger the attraction. So that means that the electrons in the first shell are more tightly bound than those in the second, than the third, than the fourth. It also means, as you can see just from this expansion, is that the electrons in the first shell are in a smaller space. So an atom encompassing only the first shell of electrons is going to be small. Atoms that have electrons in the second shell are going to be bigger than those that have only electrons in the first shell. And the same thing is true for atoms that have electrons occupied in the third and fourth shells. The atoms get bigger. So here we're showing you the other interesting thing that we get from quantum theory is that the electrons are not permitted just any energy that they want. The first shell has electrons in the lowest amount of energy because they are the most tightly attracted to the positively charged. So the energy we're talking about is potential energy. We'll describe that in more detail when we talk about energy in a later chapter. The electrons in the second shell are not as tightly bound, so they're higher in energy, and then the third shell are not nearly as tightly bound, so that's even higher, and then the fourth shell higher still. Now, within each shell, the shells are subdivided into subshells, and these are given by the labels S, P, D, and F. These will describe the shapes of the electrons that the electrons can take within these shells. We'll describe the shapes here in a little bit. Now, quantum theory predicts the following. In the first shell, only the S subshell was permitted. In the second shell, you get the same type of subshell as in the shell prior to that, which in this case is S, and then you get the next one. The new one is P. When we go to the third shell, you get the S and P subshells from the shell below it, and now the new one, D. And when we get to the fourth shell, you get the S, P, and D from the lower line shell, and now the new one, F. So you should remember the order, S, P, D, F. So you need to memorize this. And the other thing that you need to memorize is that the number of atomic orbitals. So an atomic orbital right now, you should just think of this as a region of space where we can find an electron. The number of atomic orbitals is 1 in the F subshell. There are 3 regions of space in the P subshell, so we call this 3p atomic orbitals. There are 5 distinct regions of space available for the D subshell, so 5d atomic orbitals, and then there are 7 F atomic orbitals. So again, when we count the total number of atomic orbitals that are available in a given shell, it depends on the subshell, right? So in the n=1 shell, since only the S subshell is available, and that defines only 1 atomic orbital, there's only 1 atomic orbital in the n=1 shell. In the second shell, we have S plus P. So we have 1 atomic orbital for the S, and there are 3 p orbitals for a total of 4 atomic orbitals in the n=2 shell. In the n=3 shell, we have S and P, so that's a total of 4. And now we have 5 d orbitals, so 1 plus 3 plus 5 is 9 atomic orbitals in the n=3 shell. And then in n=4, we have SPD, which is 9 atomic orbitals here. And now we add to that 7, so 9 plus 7 is 16. So what we're writing here is the total number of atomic orbitals that quantum theory predicts for each shell. Now, quantum theory also predicts that each atomic orbital can accommodate only 2 electrons. We'll talk a little bit more about what's going on with that later. But we want to now define how many electrons are permitted in each shell. Well, we take the total number of atomic orbitals, since each one can hold 2 electrons, we just multiply it by 2. And so the first shell can hold 2 electrons, the second shell can hold 8, the third shell can hold 18, and the fourth shell can hold 32 electrons. So this is showing you the maximum electron capacity for each shell. So you are responsible now for knowing what a shell is, subshell defined by these letters, and the number of atomic orbitals associated with each subshell, 1, 3, 5, 7. You need to know the total number of atomic orbitals for each shell and the total number of electrons that's permitted in each shell. All right, now one other thing that we can talk about is the electron capacity for each subshell. So an S orbital can hold 2 electrons. Since there are 3 p orbitals, 3 times 2 is 6, 5 d orbitals can hold 10 electrons total, and 7 atomic orbitals can hold 14. All right, now, one last thing. Let's go ahead and define what atomic orbitals are permitted in each shell. If we look at the n=1 shell, the only type of atomic orbital we would write is the 1s orbital. So here we're using what's called orbital notation. And we have a slide defining this later on, but I want to go ahead and talk about it now. The 1 is not counting how many orbitals you have. The 1 defines the quantum number n. So we're in the n=1 shell, and S defines the subshell type. Well, there's only 1 S is permitted in this for a total of 2 electrons. If you have an an atom with more than 2 electrons, the electrons have to go into the next higher line shell. For n=2, in here, the types of orbitals available are 2s, which has a 2 electron capacity, and the other are the p orbitals, which we now define as 2p. There are 3 of these. There are 3 2p orbitals. Since each orbital holds 2 electrons each, that's a 6 electron capacity, so again we end up with 8 electrons total. In the n=3 shell, we have a 3s orbital, we have 3p, 3p orbitals. I should have mentioned this. There are 3 2p orbitals. And now we see d orbitals for the first time. So in addition, we have 5 3d orbitals. So in the n equals 3 shell, the electrons can be arranged in 3 different subshell spaces with a total electron capacity of 2 electrons in each of these orbitals, gives you 18. And when we go to n equals 4, we're going to have 4s, 3 4p orbitals, 5 4d orbitals, and then we will have 7 4f orbitals for the first time. So this table is taken straight from your book, showing you the orbital notation, just what I've already written out, the orbitals available, and the total number of electrons in each shell, as well as the total number of electrons in each subshell. All right, so again, we're defining an atomic orbital then as a region of space where you can find the electrons, but it can hold only up to 2 electrons. So we'll either have 1 or 2 electrons. The orbitals have different sizes, so the size is defined by the shell ends. So the 1s orbital, which is in the n equals 1 shell closest to the nucleus, is smaller than the 2s orbital, which is in the higher line shell. So we see the 1s is here, a 2s orbital is going to be bigger. In both cases, the shape of the orbital is spherical. So it forms a sphere, and the probability of finding the electron is in this sphere. When we look at the shape of the p orbitals, there are 3 orientations. The shape is the same, it looks like a dumbbell. But there are 3 of these orbitals as opposed to the s orbitals where you only have 1. The different p orbitals have the same shape but are oriented along the different Cartesian axes. So they're related to one another by 90 degrees. So this is oriented along the x-axis and is called a px orbital. This one's oriented along the y-axis, py. This one's oriented along the z-axis. It's called a pz orbital, and again the 2 denotes that it's in the n equals 2 shell. If you take all 3 p orbitals together, this is what it would look like, with 90-degree angles between all 3 orbitals. So there are 3 different orientations for 3 p orbitals. When we go to the d orbitals, there are 5 different orientations that give you 5 d orbitals. Now we're not going to look at the shapes of the d orbitals. You don't need to know them for this course. For the f orbitals, there are 7 different orientations with 7 different f orbitals. So again, we're not going to show you those. You don't need to memorize those either. But again, within a subshell, what we find is a pattern. The S-type subshell can have only 1 orbital in it, and as we progress to PDF, we add 2. So we go to 1 to 3, add 2 more to go to D, we get 5, add 2 more, we go to F to get 7. So you need to memorize this. All right, now how are the electrons represented in orbitals? We can define an orbital either with a line or as a box. So we're representing this now as an s orbital, and we define electrons as arrows pointing either up or down. So I'm going to write this arrow as is now representing an electron pointing up, and the next electron we'll see has to be put in to the orbital pointing down. So what are the arrows directions representing? Well, they're representing a property called the spin of the electron. A spinning particle, or any particle that has charge that's moving, generates a magnetic field. So a spinning electron will generate a magnetic field in a direction 90 degrees to the orientation of the spin. If it's spinning to the left, we can imagine a magnetic field pointing up, and if it's spinning to the right, we can imagine a magnetic field pointing down. So that's really what they're representing. And then a rule called the Pauli exclusion principle dictates that the spins of the electrons in an orbital have to be anti-aligned with respect to one another. We call this spin pairing. So the two electrons are spin paired when we write them like this. When we go to the p orbitals, we would write our three p orbitals as three separate lines or boxes. One thing new that you need to learn here now is that orbitals within the same subshell have identical energies. So the shapes are identical too. The orientations in space are different. That's the only thing that's different about orbitals in a subshell. But their energies are identical. Now we put our electrons in to the orbitals. Each is 2 electrons each. Everything's spin paired. We have a 6 electron capacity. In the p subshell for the d orbitals, we have 5 energetically equivalent d orbitals for a total 10 electron capacity. And in the f subshell, we have 7 orbitals with a total capacity of 14 electrons. Now, we told you earlier that writing orbital notation, we put a number in front of the orbital type that defines the quantum number n, what shell it's in, and then we write a letter for the subshell that defines the shape of the orbital. So if we're looking in the n equals 4 shell, there are 4 different kinds of orbitals, s, p, d, and f. The new thing to learn here on this slide is that orbitals within the same shell, the subshells have different energies. The s subshell is lowest, the p subshell is next, so it's a little higher in energy than s. The d subshell is higher in energy than p, and the f subshell is higher than d. Again, orbitals within a subshell have the same energy. Now let's put this all together. We're showing you here the orbitals for a many electron atom. So if you were to put electrons and build an electron arrangement for an atom, you could use this diagram and put electrons in these boxes one at a time, starting at the bottom and just filling in the boxes. In fact, we're going to be doing this. This is called an electron configuration. What I really want to draw your attention to is just the nesting of the orbitals. So the first orbital, 1s, denotes the first shell, n equals 1. So only one s orbital is possible. In the n equals 2 shell, we have 2 subshells, the s and the p, with the p subshell being a little bit higher in energy than the s. I've drawn a circle around the full n equals 2 shell, there it is, which now has 2 electrons per box, would be an 8 electron total capacity. 2 electrons in the first shell, 8 in the second. When we go to the n equals 3 shell, we have s, 3 p orbitals, and now 5 3d orbitals for a total electron capacity now of 18. And then in the n equals 4 shell, we have the s, the 3 p orbitals, 5 d orbitals, and 7 f orbitals for a total electron capacity of 32. And we can just keep going on. One thing to note is that the orbital energies between shells can penetrate into one another. So, for example, for some period of time, the 4s orbitals are a little lower in energy than 3d, but this can change depending on how many electrons we have in the atom. It gets a little complicated. We're going to leave it at that for now and go ahead and move on to the next lesson, which is learning how to build the many electron arrangements using either this diagram or their periodic table. Because what you're going to see is that the order that's shown in these orbital arrangements mirrors the periodic patterns in the periodic table.